We're going to look at the binomial theorem and expanding a binomial such as this one, x plus y to the sixth power. That exponent means that it's x plus y 6 times. So if I were to do this, I would then multiply each one of these to get, I would multiply all of them together 2 at a time. I multiply these two and get x squared plus 2x y plus y squared. And then I multiply this one to that. And the result I'd multiply this towards, and the result I'd multiply this, and then so on. It's doable. I don't recommend it. It's tedious and it's very easy to make mistakes with it. So let's instead look at a different method. We're going to expand this one, and first the number of terms is plus 1 for number of terms. So there's going to be 7 terms in the answer. We're only going to look at the first 4, because if you clearly show how to get the first 4, then you would be able to continue with the patterns. This is very pattern-based. If you follow this method and follow this pattern, you can do these all the time. There's some variations to watch for, which we'll do in some of the other problems. So I'm going to call this one A and this one B. The first part of the binomial is A and the second part is B, but we're going to use X and Y, of course. The first term always has a coefficient of 1 and then takes the A term and raises it to the power that we see as the power of the binomial, which in this case is 6. Then it's the second term and it raises it to a power of 0. And that's because these two must add up, in this case, they have to add to the 6. If this had been an exponent of, say, 14, we'd have 14 and 0 because they would have to add the 14. This is an example. So that's the first term. And in fact, we would then work and multiply that out because y to the 0 is 1 and 1. And so we would come to simply x to the 6th power. Now for the second term, we're going to now have a different exponent. The exponent is automatically the exponent that we have for the binomial. We use 6. And then we're going to put the x and the y, but those exponents change. This one becomes a 5 and this one becomes a 1. So notice the 6 goes to 5 and the 0 goes to 1. So the A term always goes down 1 in each term for the exponent, and the B term always goes up 1. So we have 5 and 1, and that adds up to 6. So now for the second term, we have the 6, x to the 5th, and y to the 1st. We don't need the parentheses anymore. And there's no sign over here. That means it's plus. So it's x to the 6th plus 6xy. Now let's take a look at the third term. The third term is going to use another coefficient, and the way the pattern I'm going to show you is have 6 times 5 over 1 times 2. Well, this is 6 times 1. That's what this one was. We didn't show a 1 underneath it. I didn't before because it's an understood 1. Every number has a 1 underneath it. But because there's a 1 underneath it, I can use that on the next one and go down 1 on the numerator and up 1 in the denominator. So that's what I wanted you to see here. Let's now erase that part of the green one. And then we're going to do these exponents again, x, but now down 1, and y up 1. So from 5 to 4, and from 1 to 2, and it still adds up to 6. And here in this, the 2 goes into the 6 3 times. 3 times 5 is 15, and we have x to the 4th and y squared. Oh, and it's going to be plus because there's no minus there, so it's always that means it's adding between them. As it is that first term plus the second term plus the third term, unless a minus were to make it a negative. Now let's look at the fourth term. So we have a couple of patterns that we're going to base this on. the pattern of the coefficient first. Here, it was 6 times 5 and 1 times 2 because we went down 1 and up 1. We'll do the same thing here. 6 times 5 times 4. Underneath it, 1 times 2 times 3. And then x and y, and the coefficient or the power of the x will be down 1, and the power of the y will go up 1. Ooh, they're both 3s now, and they add up to 6. And now let's look. 2 times 3 is 6, which cancels that out. 5 times 4, therefore, is 20, plus 20, x to the third, y to the third. So for the final answer, I'll put these together in a neater, normal writing way with normal spacing. And those are the first 4 terms. If I did 3 more, I'd get all of them, but right now I'm only going to go through doing that. Let's put those 2 coefficients or exponents back. This was 5 and 1. So x to the 6th, x to the 5th. We don't really need the 1 for the y, but sometimes I'll do it. 4 and 2, 3 and 3. Now, before I move on, let's look at these coefficients and the one that's here, of course. Another way to get them besides doing what I did is to use Pascal's triangle. What Pascal's triangle is a pattern-based thing and in a pyramid triangle type of thing. Watch what I do, and if you haven't seen this already, you'll see that you're adding up the 2 numbers above so that diagonally it makes a new number underneath. 1, 5, 10, 1, 1, 6, 15, 20, 15, 6, and 1. Notice this row. Whoops, I didn't want this to disappear. Let's bring it back. That row, 1, 6, 15, 20, 15, 6, and 1, is 1, 6, 15, 20, and if I kept going, it would have been the 15, 6, and 1. So that is one way to get the coefficients that go in front of the x's and the y's, or the a and b, whatever it is. So you can use that method, but notice you have to make out this triangle. If you're doing a power such as 6th power, or 7th power, 8th power, or even a 10th power, this isn't so bad to do. But if you have to do the 23rd power, making this whole big, huge triangle is probably, well, very simply doing this method is probably simpler than writing out the triangle to like the 23rd level. Up to you, save time, do it the way that I'm showing you with the pattern here. Now let's look at one where there's difference. Here's the big difference, is that there's a coefficient in front of the x. Well, I am actually going to follow the same patterns. Watch and follow along. The first term is going to be the coefficient 1, and then whatever the a is to the 7th power, because we have a 7 here. And so the a is that whole thing, 2 and x together. That's a. And then b, of course, would be, in this case, just the y to the 0 power, plus I have to use the same, whatever the coefficient, whatever the exponent is the second coefficient. And then it's 2x to the 6th power, and it's y to the 1st power, plus now I will do my thing with the numerator, down 1 and up 1, because that's really a 7 over 1. So now it's 7 times 6 and 1 times 2. 2x to the 5th power and y to the 2nd, plus 7 times 6 times 5, 1 times 2 times 3. I like the pattern, it makes sense. Oops, that's not 3, it's x to the 4th power and y to the 3rd power. And that would be 4 terms. Now let's actually, here's the 2nd, 3rd, and 4th term. Now let's clean it up. Well, first thing I see is that 2 and 7, that's 2 to the 7th as well as x to the 7th. That's something to watch out for. If it's inside the parentheses or it's with the x, then the 2 also has to be raised to the 7th power. Over here, we're going to have 7 times 2 to the 6th power, x to the 6th, and a y. So I'll multiply those in just a moment. 2 goes into 6 3 times, so we have a 21 there. And then we have times 2 to the 5th power, x to the 5th power, y squared. Here, the 2 and the 3 multiply to make 6, so they cancel that out. So it looks like we'll have a 35, 7 times 5 is what's left there, times 2 to the 4th power, x to the 4th power, and y cubed. Between each of these, it's adding, because there's nothing to make them negative right now. Okay, and now we can clean up what those numbers are going to be. And first, I'll point out then that 2 to the 7th is a 128, 2 to the 6th is 64, 2 to the 5th is 32, 2 to the 4th is 16. So here we have 128 x to the 7th. This is going to be 7 times 64, which is 448 x to the 6th y. 32 times 21 is 672 x to the 5th and y to the 2nd to finish that one. And here it's 35 times 16, which is 560. And now it's x to the 4th, y cubed. Let me circle that. Those are the first 4 terms. Now, this was an example to show you how numbers that are in A or in B also have to be used with the exponents when it's appropriate. Here we had a 7 and 0 adds up to 7, 6 and 1 adds up to 7, 5 and 2 adds up to 7, 4 and 3 adds up to 7. But each time that the 2 is in there, it has to be raised to the power that the x is also. And that's why our numbers no longer match the Pythagorean theorem. Not Pythagorean, my mistake, the Pascal's triangle. This 1 and 7 and 21 and 35, those do match the Pascal's triangle, but the final answer has other numbers multiplied to those. So the final answer uses, I guess you could say, Pascal's triangle and numbers raised to a power. So that's a variation here. Let's take a look at another variation, this time where there's a negative. And this time it's to the 12th power. The patterns, we're still going to do exactly the same, but watch closely what happens with the negative here. First term, a 1, of course, and then the 3x raised to the 12th power, and then negative y to the 0. See how I deal with that negative? I put it with the y and keep it with it. It doesn't mean anything here because negative y to the 0 is still a 1. So we're going to have 3 to the 12th and x to the 12th because 1 times 1 for the others. Well, let's continue on. The second term is going to be the exponent 12, the 3 times x raised to the 11th power, and the negative y raised to the 1st power. So before I go to the next one, let's follow what's going to happen here. That's going to be a 12 times 3 to the 11th, x to the 11th, times this negative is a negative 1 that'll be raised to the 1st power, and then a y to the 1st power. So we have a negative there that, because that's a negative 1 times y, that's really what it is. It's raised to the 1st power, and that means that negative is going to make this thing negative over here. So to sort of continue with it, well, I'll multiply that, come back to that, because we're going to do it. We have 3 to the 11th. I guess I could continue with what that is here. If I do 3 to the 11th times 12 times negative 1, I would get negative 2,125,764 x to the 11th y. So that's 2,125,764, but it's negative. And this one, we have the x to the 12th, and 3 to the 12th is 531,441. So we have 531,441 times x to the 12th minus 2,125,764 x to the 11th y. And now let's do the third term. So for the third term, I'm going to do the 12 times 11 and 1 times 2. If you do Pascal's triangle, that would work. You could multiply that out or do that whole pyramid. but I find it easier to do this. 212, 6, we get a 66 for that part. So we're going to have a plus 66, but now we have 3x, and before it was 3x to the 11th, so now it's going to be 3x to the 10th power, and negative y squared. So we're going to have 66 times 3 to the 10th, x to the 10th, but a negative y times a negative y will become a positive y squared. So in this case, the negative here will cancel out because it's being squared. So it's negative 1 times negative 1, and so you get a positive 1. So here we would multiply the 66 times 3 to the 10th power, and that comes to 3 million, and it's plus this time because that negative canceled out. 3,897,234 x to the 10th y squared. And the 10 and 2 again add up to 12. Okay, now let's do the fourth term. So we're going to follow the same pattern, 12, 11, 10. Underneath it, 1 times 2 times 3. 3x to the 9th power and negative y to the 3rd power. Well, now let's look at these numbers. 2 times 3 makes a 6. 6 goes into 12 2 times. So we have 100, let's see, 110 times 2, 220. So this, all of the coefficient part becomes 220 times 3 to the 9th power times x to the 9th times negative 1 to the 3rd, and then y to the 3rd. That negative 1 to a 3rd is negative 1 times negative 1, which becomes a positive 1, times another negative 1, that's a negative 1. So that negative 1 is going to make this plus minus. And then 220 times 3 to the 9th power comes to 4,330,260 x to the 9th. Bring that back, get that 0 in there. X to the 9th, y to the 3rd. Ooh, there's a lot to that one. And each time the exponents add up to 12, and the coefficients are a combination of the coefficient and the numbers that are multiplied out. So let's go over this set again. So here, the way I got the numbers for this one was the 12 times 11 times 10 over 1 times 2 times 3. And then there was a 3 to the 9th power and the x to the 9th power, but I'll hold off again for a moment on that. And the negative 1 to the 3rd, and then I'll put these, x to the 9th and y to the 3rd. So one of the things is to see this as negative 1 times y to the 3rd power. And that makes it easier to see that's negative 1 to the 3rd and y to the 3rd. So this part here, let's see what we do with those numbers. And that's where the 2 goes into the 12 to make it a 6, the 3 goes into the 6 to make it a 2, one way or another. 2 times 11 is 22, times 10, that's 210. And then 3 to the 9th power, I would write that out, but it's actually easier just to say 3 to the 9th. And then I would make that, I would do that in the calculator, times negative 1. Here we have negative 1 times negative 1 times negative 1. These two become positive 1 times negative 1. So it's times negative 1. So that negative I'll put in front, and then 210 times 3 to the 9th power in the calculator. That's where you get 4,330,260. That's how I got the exponent and for the coefficient, because it's a combination of 3 things this time. It's a combination of that pattern. It's a combination of the 3 that's raised to the 9th power and the negative 1 that's raised to the 3rd power. Even though the negative 1 only simply just changes the negative, but that's enough to make a difference, to make it right. right, let's take a look at another variation now. The last one of these where now it's going to be a negative and the coefficient both in the y, the second term. All right, so now let's take a look and do the same kind of pattern. First, 1, x to the 14th. I won't talk quite as much going through it, but I will show these steps. Plus second term, supposed to be md there. Okay, second term. I use the 14 automatically, down 1 on that exponent, up 1 on that exponent, plus, now the third term, 14 times 13, 1 times 2. Since there's a 1 underneath here, just unseen most of the time. Down 1 and up 1 in the numerator and denominator. X to the 12th, negative 2y squared. Ooh, I'm running out of room, so I'm going to write a little bit smaller for the fourth term. 14 times 13 times 12, 1 times 2 times 3, x to the 11th, negative 2y to the third. All right, now let's look at these numbers. This is just 1 times 1. We get just x to the 14th there. Here we're going to get 14. So I'll do 14. Nothing there, and I'm going to get a negative 2 to multiply it to it. X to the 13th and y to the first. I don't need to put the 1. I guess I will. That adds up to 14, which I want. And here we'll get a negative 28. So if I go that next step, remember that it's negative 28 x to the 13th y. Now for the third one, 2 goes into 14 7 times. So we have 7 times 13, which comes actually to a 91. And then we have the x to the 12th, but, well, I guess I could do x to the 12th, and then the negative 2 squared, and y squared. Well, negative 2 times negative 2 is a 4, so we get 4 times 91, and 4 times 91, or I'll do it this way, 91 times 4, and that gives us 364, and then the x to the 12th and the y squared. So it gives me those two things, the 4 and the 91, and I get the third term. For the fourth term, the 2 and the 3, couple of ways we can play with this. What I'm going to do is that 2 times 3 is 6, and 6 goes into 12 2 times. So if I do that, I have a 14 times a 13 times a 2. Okay. So I'm going to have, in fact, I'll do plus 14 times 13 times 2. And here we have negative 2 cubed. Well, negative 2 times negative 2 times negative 2 is a negative 8. And then we have x to the 11th and y cubed. So the negative makes this one minus, and 14 times 13 times 2 times negative 8 comes to 2,912 x to the 11th y cubed. This all the way around. That's 4 terms, 2 of them negative, because when it's an odd exponent, there'll be an extra negative each time, so it makes those terms negative. And then the coefficients times the numbers to the powers gives you the actual numbers for the correct final coefficients. Let's go now and look at when we have to find one particular term. There's a formula for this. You could, if you want to find, say, the 10th term of a 14 power binomial, you could multiply the whole thing out or do the expansion like I showed before. But that's a lot of work. You could do it for more than 4 times, but it also is good to have a formula where you can go directly to just that one single thing. So take as an example a plus b to the nth power. We don't know what n is yet, but by using those letters, we'll be able to show what the formula is. So here is the power, And what we do for the coefficient is we use what's called a combination. N to the n factorial over n minus k factorial and k factorial. And then it's a to the n minus k power. And then it's b to the k power. Now let me tell you what each of these things are. So n is the main exponent. I would like to make that the kind of n like textbooks do. Okay. So n is the main exponent. K is 1 less than the term you want. So if n was 27 and I wanted to know the 20th term, k would be 19. If I wanted to know the 15th term, k would be 14. It's 1 less. Now, A and B here are the parts. That's easy because A and B come from the parts of the binomial, the first term or the second term of the binomial. But N and K are the ones that you have to watch for what they mean. So let's go through and do an example for one of these here. We're going to find the 5th term. Immediately, I know K is 1 less. K is 4. In the expansion of x plus y to the 10th power, and immediately I know that's n. So I'm going to follow this pattern here. And that means it's going to be 10 factorial. And then it's going to be n minus k, or 10 minus 4 factorial. And then 4 factorial. And then a is x, so it's going to be x raised to the 10 minus 4 power. And it's going to be y raised to the 4th power. Well, remember that factorial means each of the numbers below it, 10, multiplying them all out, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Multiply all that out, and that's what 10 factorial is. We're going to shortcut that a little bit. This part, 10 minus 4 factorial, would be 6 factorial. So I'm going to take the 10 and I'm going to do 10 times 9 times 8 times 7 times 6 factorial. And underneath it, I'll put 6 factorial. And then the 4 one I'll show up all the numbers. 4 times 3 times 2. We don't really have to put 1. Well, what I want to show you is that this is 6, 5, 4, 3, 2, 1. And this is 6, 5, 4, 3, 2, 1. So we'll just cross out 6, 5, 4, 3, 2, 1 all at once. This 4, 3, 2, 1 is a different one because this one's different from that. So this 6, 5, 4, 3, 2, 1 just cancels out. And now I can cancel some other things. Whoa. So I got back there. Now you should see the screen again, the correct one. So I'm going to look at these numbers and I see 4 times 2 makes 8. So I can just cancel that out. And 3 goes into 9 3 times. Oh, that's nice. That works out nicely. So what I have here is 10 times 3 times 7. And then over here, for these things, I have x to the 6th power and y to the 4th. Notice 6 plus 4 adds up to the 10 there. So 3 times 7 is 21, times 10 gives me 210, x to the 6th, y to the 4th. And that would be the 5th term. So you can also use a calculator to do that. It has to be in, let's see, some scientific calculators have factorial on them. Some of them do not. The graphing calculators have this as well. But this is a way, and relatively easy way to do it by hand, because then a calculator you just multiply 10 times 3 times 7, or you can do that in your head. Now let's look at one which will be a little different. In this case, has a coefficient of A or B here. All right, so that's A, that's B, 12 is N, and if we want to find the 8th term, that means K is equal to 7. Okay. So we now know those things. Now let's use that formula. The formula was n factorial over n minus k factorial, a, b first, when it should be, a to the n minus k and b to the k. So I'm going to fill in those things. N factorial, that's 12 factorial. And then it's going to be 12 minus 7 factorial and 7 factorial. And then it's going to be instead of a, what I'm writing is 2x. It's 2x to the n minus k, and then it's y to the k. So I'm going to do, well, this comes to 5 factorial. So I'm going to do 12 times 11 times 10 times 9 times 8 times 7 factorial. 5 times 4 times 3 times 2 times 1 times 7 factorial. That's this one. These all cancel out. So the 7, 6, 5, 4, 3, 2, 1 and those go away. And on these others, I think I can work with these. So what I can do is, let's see, 4 times 3 is 12. There goes that 12. 5 times 2 is 10. There goes that 10. So number-wise, I have 11 times 9 times 8. But now let's look at this. That is, oh, I made a mistake. I don't know if anyone caught it, but let's fix it right now. This is supposed to be k for there, which means that's 7. This one, when it's the 12 minus 7 or n minus k, that's 5. Now I have those correct. So what we have is 2 to the 5th power and x to the 5th power and y to the 7th. So I have to do 2 to the 5th power. So 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th is 32. So we're going to multiply by 32 there and have x to the 5th and y to the 7th. So our answer for this, when we do 11 times 9 times 8 times 32, is 25,344 x to the 5th, y to the 7th. And that is the 8th term. So in this lesson, you see how to expand a binomial using the patterns for the coefficients and the exponents. And you've seen how to find a specific term using this formula and using it in both cases, both types of things, using it as a coefficient with the a or b inside the binomial, or a negative, depending on what the case is. I hope this helps. Thanks for watching.